Hello, everybody. We welcome you at this our last lecture for 2021. We appreciate the time you took here to attend this lecture, and it sounds to be a very interesting, very exciting topic that Jean-Philippe Tetienne will present today. And I would like to say a few words about Jean-Philippe background. So Jean-Philippe did his PhD in France under the supervision of Vincent Jacques, where he realized the first scanning NV microscope for application in nanomagnetism. In 2015, Jean-Philippe joined University at Melbourne, Australia, particularly the group of Lloyd Hollenberg, where he has been developing the technology and applications of Widefield and the microscopy. So he continued his topics of his PhD work, it seems. Last year, Jean-Philippe started his own group at MIT University in Melbourne to continue the work on NV microscopy and explore new material systems for quantum sensing, in particular with spin defects in hexagonal boron nitride. So Jean-Philippe, the stage is yours.
Thank you, Olga. So I'll be talking about quantum diamond microscopy. So what do I mean by quantum diamond microscopy? Typically, it refers to imaging techniques that use the NV center in diamond as a sensor. So we call it a quantum sensor because we probe energy levels of the spin structure, as you can see in that schematic here. And we do that by doing ODMR, optically detected magnetic resonance. And those energy levels depend on quantities such as the magnetic field, electric field, strain, temperature. And so by probing those energy levels, we access those quantities. So that's the sensor aspect. But what about the microscopy? How do you make a microscope out of that? So you have two approaches. On the left, this is a scanning probe approach, where you have a single NV, typically in some kind of tip, diamond tip, for instance, that you scan relative to the sample to form an image pixel by pixel. And on the right, this is a wide field approach, and that's what I'll be focusing on in this talk. This is when you use a slab of diamonds and you form a layer of NV centers at the bottom here facing the sample. So it's mechanically static, there's no scanning, and the way you make an image is by illuminating a wide region of that NV layer and imaging the response with a camera. So you get an image in a single shot in that way. So what are the differences and pros and cons of those two approaches? So you see here a kind of direct comparison of the kind of images you get. So the main difference is a spatial resolution and field of view. So you see on the left, this is an example image from the group of Patrick Meletinsky in Basel, where here it's an image of a 2D magnetic material. And you see it's very high resolution, spatial resolution, typically 15 nanometers. The field of view is a few microns, 10, 20 microns, typically at most tens of microns. In contrast, the wide field approach is lower resolution. So at best, you're limited by diffraction, so 500 nanometers. But you get a much larger field of view. So here it's about 100 micron. And you can get up to millimeters field of view. So other differences, the sensitivity, and that's because you do parallel imaging in wide field as opposed to you have to scan pixel by pixel on the left. So you get typically a few orders of magnitude difference. So that's for the performance, if you like, comparison. But there is another aspect that is very important. It's how easy the techniques are to use. And kind of paradoxically, the scanning approach, even though it's more complex, it's been developed in a way that it's relatively easy to use nowadays. And you even have commercial systems. The example here is the one from QNAMI, where you don't have to be a diamond expert, essentially. You put your sample in, after some training, you can get image relatively easy. And that's a bit contrasting with the Widefield approach, which is kind of lagging in terms of commercial development. So we have prototypes, especially from the Widefield group, but it's still not a very easy to use technique, as in you need some kind of diamond expertise because you need to handle diamonds and things like that. And I'll talk more about that. So why do we care? Why it's still an interesting technique that we want to develop? So the key strength, I'll summarize here. So compared to other techniques, for instance, to image magnetic fields, it is quantitative. So it's very useful for a lot of material studies. It is sensitive, more sensitive than many other magnetic imaging techniques and more sensitive than scanning NV, for instance. And it's also quite versatile. You can do multimodal imaging. For instance, for magnetic fields, you can do spectroscopy up to gigahertz frequencies. So that opens a lot of sensing modalities. Now, in terms of the specific applications, the big one is to magnetic materials by doing magnetic field imaging in different contexts, from biomagnetism to rock magnetism for paleomagnetism, and also looking at synthetic magnets would be maybe the main application, so solid state magnetism. But you have some other applications in electronics, so probing charge currents, and that can be static, but also fluctuating charge noise or microwave circuits, things like that. You can do chemical analysis. So this is an MRI image as an example. And maybe more of a niche application, but there are also interesting opportunities in diamond science, probing internal electric field and strain fields to learn about diamond material or diamond devices, for instance. So in this talk, I'll talk about some of the challenges, technical challenges of that technique that we need to address in order to progress the technology to a stage where maybe it could become commercial, or at least that can deploy a bit more widely in non-diamond labs. So first challenge, I call it the interfacing challenge, and I'll present an approach that we developed recently. There's also an ongoing materials challenge around the performance quality of the diamond sensor we have, and how we create them, and the availability of those materials as well. I'll talk about also cryogenic operation that was somewhat important for application that we've developed as well, and I'll finish with a bit of an outlook. So what is this interfacing challenge? So in Widefield microscopy and the microscopy, you need to interface a large piece of diamond with the sample that you want to image. And so you have two approaches. One is to drop the diamond on the sample. So you put it NV face down and you just drop it. As you can see from that schematic here, depending on how flat the surfaces are, you may get some standoff, or it may not sit flat. So that's the main downside of that approach. It's also still not super convenient. It sounds like it is, you just drop the diamond. In practice, it takes a bit of practice to be able to get the diamond where you want it. And the picture here shows an example. You have a piece of silicone, you have some kind of magnetic thin film prepared on that sample that you can't really see, and you put the diamond down. And you see the diamond here, it's this one is a 2 by 1 millimeter chip also. And you see fringes actually in that diamond. That means there is an angle. You have interferences, so there's going to be some kind of angle. And that's often what you get. So you don't get the diamond sitting nice and flat. In general, you have to try a few times until it's in the right position. You also notice there is some glue here in the corner. So it's not mandatory, but in practice, we found that it's the best way to get the best standoff. And if you start putting glue, it's quite destructive. You destroy your sample, and it's also hard to recover your diamond. You can, but it's still quite invasive. So it's not a super convenient technique in general. And that's why it's good in a diamond lab. But outside a diamond lab, it takes a lot of training and skills that you don't really want to have to go through. There is another approach, which is where you fabricate the sample directly on the diamond. So that's not always possible, but sometimes you can. For instance, here, you see on that photo here, you have small fragments of some kind of magnetic materials. Here it's 2D flakes of some magnetic material that we could spin coat directly on the diamond, or transfer. So you have different techniques to transfer samples. So when you can, then it's a convenient. It's a good technique because you solve the standoff issue. So here the sample sits directly flat, so you don't have that standoff issue or flatness angular issue here. And you see the diamond here, it's a 2x2 millimeter chip. We fabricate typically a metallic grid just to facilitate spatial correlation down the road. So none of those techniques are really convenient to use. The fabrication on diamond, it's even worse in the sense that you have to learn how to fabricate or prepare samples on diamond. So again, that's not something you want to do outside the diamond lab. So we're kind of missing a convenient way of interfacing the sample with a diamond. So that's what we've addressed recently. So we've come up with that concept, which is pretty obvious. We call it an integrated Widefield probe. And that's to say that we put the diamonds on some kind of arm, and we also integrate the microwave into that probe. And that's where we keep it separate from the sample at all times. There's no direct mechanical contact, and that's where you can exchange the sample much more easily. So in practice, that's how it looks. You see there is a PCB, which is 5 by 5 millimeter or so. And that PCB has a microwave loop. So that delivers the microwave that you need for the measurement. There's a hole in that PCB, so you can image through. We put a glass cover slip to cover the hole, and we glue the diamond in the middle here. And you see on the side view photo here, there's this arm, this copper arm sticking out, the PCB, and you see the little red dot. It's red because it's glowing. It's a PL from under green illumination. And the sample, you place it underneath, and then you can approach it. And that's where you can you keep the probe in place at all times, and you can exchange a sample relatively easily, much more like a scanning NV or any kind of scanning probe microscopy. So that brings you the convenience that you don't need to handle the diamonds. Now, there's no scanning, so it's still static. You need to bring the sample close enough, and then you can take an image. There's no scanning, so it's still quite simple in terms of instrumentations around it, but it's a similar concept. So to test that idea, we've custom built that Widefield microscope, very standard. There is a laser coming from the top. You collect the PL and you image with a camera. And in the middle here, this is where the action is happening. You have this probe, this arm sticking out. And in the middle, you put a sample on the sample stage. And the arm is placed on the stage, ergonometer stage, so you can control the angle. So you can adjust the angle without translating to get the probe parallel to the sample. So to test that system, we've used that sample here, which is a magnetic sample. It's a piece of silicon. It's a few millimeter in size. And there is a very thin, 1 nanometer, in fact, thin film of cobalt iron boron, which is a perpendicularly magnetized magnet. And it's been patterned in this type of shape. You get large pads and strips in between. So how do we actually align that probe? So you place the diamond roughly in focus, and you get a PL image. And then how do you know where to go and how to approach the sample? So first of all, you approach it and you start seeing fringes. And that's because if there is any kind of angle, you have interferences between reflection from the diamond air surface versus reflection from the air sample surface. And that gives you fringes. And the more of an angle, the shorter the periodicity of those fringes is. So it's hard to see those fringes in a static image, but when you do it in live and adjust the angle, you see them pretty easily. So here I put a guide just to show where they are, but it's not super easy to see in the static images. So typically you bring your sample, you start seeing those fringes like that, and then you use the angular control to increase the spacing between the fringes. So you go from the top situation to the bottom situation, and you try to space them as much as possible, which means you're parallel now. And once you're parallel, then you can push the sample up until you see that it's touching. It's pretty easy to see that you have a contact. If you don't do that, if you keep the angle and try to brute force the sample into the diamond, it doesn't work. It doesn't actually get you the flatness. You just push everything up, but it doesn't get flat. So you have to get the angle right first and then approach and get the contact. So once you do that, in each case, you can get a magnetic field image. So you do ODMR, scan microwave-frequency, do the processing, etc. I won't go into detail, but you get this kind of magnetic field image. This is BNV, which is a projection of the field along the NV axis. And you see that in the top case, you get a somewhat blurry image. In the bottom, it's much sharper. And again, it's very reproducible. As long as you get the angle right to start with, then you push and you get a sharp image. If you try to brute force it without the angle first, it doesn't work. It's always blurry. So it gives you a quite reliable method to get a sharp image, to get a good standoff. And it's also better than just dropping the diamond. If you were to not use the arm, but just dropping a diamond, letting it loose, typically you get the top situation more often than not. You have to be lucky or to try quite a few times to get a sharp image. So this one is more controlled. This approach is much more controlled. It's quite reliably giving you sharp images. So how to quantify how good the standoff is? So for that, this is another example of an image we got. We compare to analytical function for the magnetic field from such a magnet. So here we take the large pad and it's all analytical. You can predict the function of the stray field across an edge. And you see here the data and the fitting and the fit parameters. So we include the thickness of the NV layer here. And basically the only fit parameter is the standoff. So from surface to surface. And the histogram here is shown here. We get a mean standoff of 1.6 micrometers in that case. So that's pretty good. It's not diffraction limited. Diffraction would be less than a micron, definitely in that case. But it's still pretty good and similar to what you have when you drop the diamond and try 10 times and you get lucky eventually, you get that. You don't get better than that. So we get reliably that value as opposed to get it randomly by luck. We still want to improve on that, but it's a pretty promising result and it gives you still quite useful images. I would also note that we haven't taken too much care of cleaning the surfaces. So you see the sample is pretty dirty. And you see the PL image also show a lot of features. The diamond also is clean, but it's in a normal environment. So you'll have dust around. So it seems that the approach of getting the angle and pushing actually helped with making sure there's no dust particle in between. But still, we think we can do better if we get the things cleaner and flatter. I suppose you can do better. So I haven't spoke about materials yet. So what kind of diamond are we using? So I'll talk more about that in a few slides, but just to give you already an idea. So here we use this type of type 1B HPHT diamond, and we create an NV layer in it. And we laser cut them to size. So basically you want to match the size of the diamond with the side of the field of view you're aiming for. There's no point having bigger of a diamond because it's going to actually make it harder to get a standoff that is small. So we cut it to size, so it's a bit less than a millimeter square or so, and you see it glued here. And the good thing is, even though it's small, so not super easy to handle, because it's permanently attached to the probe, you don't have to worry about it anymore later. So that brings me to the next part, which is the materials challenge part, so to speak. So I'll briefly go through some of the techniques that we use in the context of wide-field microscopy to create those NV layer, and I'll show a bit of a comparison of how those techniques differ. So what are the design parameters that we care about in wide field? So the overall size of the diamond, so lateral size, I've just mentioned, you want it small, you want to match your field of view essentially. Diamond thickness, it's okay to have a thickish diamond, but if you want really to get the diffraction limit, you worry about aberrations, optical aberrations. So you want a thin diamond, ideally as thin as possible. 100 micron is good, 50 micron. Less than that, it's very hard to handle. But yeah, 100 micron is ideal. But if you're not pushing towards a very high resolution, then you can get a more standard 500 micron thickness, if you like. So more importantly for wide field application, very important parameters are the NV layer thickness, the standoff to the surface. That's typically you want that to be 0. There's very little reasons to actually have a standoff, so typically it's directly at the surface. And the NV density is also an important parameter. And those two, thickness and NV density, will depend on the application. So there's no general requirement. It will depend how you're going to do the experiment and what the application is. Precisely, those are the 3 types of regimes you can distinguish of NV layer thickness. So on the left, this is when you're trying to detect fluctuating signals, so magnetic noise, for instance, from ions, molecules. And in that case, the signals decay quite rapidly with distance from the sensor. And so that means you want a thin NV layer that is directly at the surface. And thin would be something like 10 nanometers in general, is ideal. So that's very thin. Now, more often, we're looking at imaging static fields, magnetic fields, for instance. And in that case, the decay of the signal is kind of irrelevant. And so in that case, you want to pack more NVs in. And so you're going to do a thicker NV layers, because if it doesn't affect the measurements in any way, you might as well put more NVs, because you'll get a better sensitivity. And so here you want as thick as your spatial resolution will be. And so if your spatial resolution is close to diffraction, then you want a few hundreds of nanometers thickness, or up to a micron, depending on what your diffraction limit is. So most commonly in wide field, you want an NV layer thickness between 100 nanometer and a micron or so. And in that way, you can be close to the diffraction limit. Now, sometimes you can actually get away with a thicker NV layer when either your sample is further away for some reason, or because the source of the magnetic field is buried into, for instance, a slice of some sample, a rock or biological material, something like that, where if you have some magnetic nanoparticles buried several microns away, then there's no point having too thin of an NV layer, so might as well have it thick. And so that can be tens of micrometers in thickness would be the ideal thickness for some applications. Another application is when you measure charge currents in a semiconductor, for instance, where the currents could be in 3D, so it could extend in Z over several microns. So again, in that case, there's no point being too thick. So you see that we've got several orders of magnitude variation in the requirements. And of course, that's going to have impact on what's the best technique to create those NV layers. So I'll say more about each of those, but in summary, for thin layers, nitrogen implantation of a CVD pure diamond is typically the most convenient technique. On the thick side, delta doping or nitrogen doped CVD growth is the most appropriate technique. You can choose the thickness quite flexibly. And when you're in between, this is where you have more of a choice. You can use either one of those, or you can use also ion irradiated type 1b, HPHT. And so it's in this regime, which is maybe the most common one for wide field applications, that it's a question whether which one is best and what are the pros and cons, which one is best in terms of performance and then in terms of convenience, etc. So I'll say more about each of those. So the first one is nitrogen implanted CBD. So this is where you start from a pure, say, electronic grade CBD diamond. You implant some nitrogen containing species, N plus, Cn minus. You anneal and you get your NV layer. It sounds like a very convenient technique because you can choose the energy and the fluence to control basically thickness, depth, and density. Now, it's not that true in practice. It's a good technique for shallow layers, but less so for deeper layers. So for shallow, for instance, this graph is a stream simulation of a 6 kV nitrogen implant. So you see in red, this is the nitrogen profile. So here we choose a fluence to get a 50 ppm maximum density, and that's between 0 and 20 nanometer depth. And in blue, this is a vacancy profile. So at the peak, you have 500 ppm of vacancies. So that's a ratio of 10 vacancies for each nitrogen. So it's a pretty good ratio. So once you anneal, you'll get some NVs, and you won't get too many vacancies left. They will form some divacancies or vacancy clusters. You anneal a lot of them out, but it's still a pretty good NV layer as far as quality and spin covariance goes. The issue is when you try to go deeper, this is where the damage, as illustrated here, especially around where the nitrogen ends up, becomes very bad in comparison. So this, again, stream simulation shows a case of a 100 kV nitrogen implant. If you aim for 50 ppm at the peak, you get 5,000 ppm of vacancies. And that's a lot of damage, that's 0.5%, right? So first of all, you won't get as many NVs, and you'll get much more residual damage, because that's so much damage that you're gonna have a lot that's gonna stay in your crystal. You're not gonna anneal it out, and that's gonna limit your T2s. And the other thing is, you see that this distribution is somewhat peaked. So it's wider than before, but it's still quite deep and peaked. And the issue is you can't really use that region here because it's pretty dead now. You have so much damage that if you try to put more nitrogen in, well, sure, you get more NVs, but it's going to be worse and worse as far as T2s go. So overall, it's not a good technique if you try to go a bit deeper than 10, 20 nanometers. The cost is also something to consider. You start from a costly material, so obviously that's also an important aspect. So in this regime of hundreds of nanometers, there is actually a quite convenient technique, which is when you start from an HPHT type 1b diamond, so very inexpensive, and you irradiate with ions to create that NV layer. So the thing about type 1b is they have a lot of nitrogen, but in fact not many NVs. At least from a Widefield application point of view, it's kind of negligible. You don't see them on a camera in normal, typical Widefield imaging conditions. And so it's that means it's a good material to start with. You just want to create NVs locally at the surface, and you do that by creating vacancies locally, and you do that with ions, ion implantation. So you can implant any species you want. It can be light ions, helium, carbon, or heavier ions, and you create your vacancies. You anneal, you get your NV layer. The simulation here shows a depth profile of the vacancies for different carbon implants energies. So 10 kV, you get a shallow layer, 100 kV, 100 nanometers or so. And then if you go deeper, you get a more and more peaked distribution. That is also more and more deep. So that's not great if you want a uniform thick layer. So in that case, you want to actually use heavier ions. And so an example is if you're aiming for 1 micron thick NV layers, that's kind of the regimes that I say was typical for Widefield. You can use, for instance, antimony. This is a purple curve, which gives you a somewhat flat distribution. Flat as in there's a factor 2 between the max and the minimum here. So it's relatively uniform. So if you want a 1 micron layer, you just implant antimony at a few mega electron volts, you anneal, and you get your NV layer. So it's actually relatively convenient in that regime. From 100 nanometer, you can use carbon, to 1 micron, you can use heavier ions, or you can use heavy ions no matter what, if you like. Beyond 1 micron, it's harder because you get peaked distribution. So it means you need to do multi-energy implantation, and also 10 MeV or multiple MeV. It's harder to get a source that gives you that. So it's not so accessible for beyond 1 micron. So between 100 nanometer and 1 micron is a very convenient technique. So the example shown here, so we start from, and that's the example that I showed before that we use for the Widefield probe work. We start from those materials that are, so 4x4 mil plates. They are 400 micron thick, and they cost $50 a piece, so very cheap. So this is from a Chinese company, Chengwang, I think it's called. So it costs basically nothing. The issue is you've got a lot of sectors. You see the yellow, different shades of yellow. And so once you implant and you anneal, so here we implanted with 1 MeV antimony to get this 1 micron or so NV layer. And this is a PL image afterwards. So you see clearly it's correlated with a shade of yellow. It's not actually trivially correlated. If it's too yellow, you get actually less PL because then you have tunneling when you optically excite. So you don't want actually the super yellow one. You want the more less colored sectors. So one limit is you're restricted by your crystal and your sector that you have to start with. But if you have a laser cutting machine, then you just go in and cut exactly where you have a good sector. So it's adding a few extra steps, but once you have that, you have plenty of those pieces, you pick the best pieces, you can characterize them, there's a sensitivity, and then you can use those for sensing. And that's exactly what we did in that work. We picked a good one and we use that. So overall, it's still quite cost effective, but you don't have much control on the nitrogen density and on the sectors, so there's a bit of randomness involved. And this is where it comes in the last technique, which is the nitrogen-doped CBD growth, or delta-doped as it's often referred to. Here you start from an E-grade CBD, you grow and incorporate the nitrogen during the CBD growth, and you grow however thick you want, and that's the main advantage of that technique. And then you activate those nitrogen to get more NVs out by either ion irradiation or electrons. It doesn't have to be localized, so it could be electrons in that case, and you get your NV there. So in principle, it sounds very flexible. You get the nitrogen density you want, the thickness you want. In practice, CBD is always takes a lot of work to get reliability out, but in principle, this is the most flexible technique. And especially if you're on 10 micron thick layer, that's basically the best technique to get a uniform layer. Too thin layers are harder to get, say 10, 20 nanometers. It's hard to get it homogeneous, to get a homogeneous nitrogen incorporation. So typically it's going to be more for at least 100 nanometer thickness to get a good uniform layer. Now, one issue is growth still is not perfect, and you're going to have strain, you're going to have defect, and especially you're going to have surface morphology imperfections. And you see here two bad examples that I've chosen to illustrate that. In this one, you see a lot of streaks, sort of surface roughness. In the right, it's even worse. You get tens of micron scale growth defect pyramids. So clearly that's going to be an issue for Widefield where you want a short standoff. So you want to interface with a sample, that's going to be an issue. So it's still something that is hard to get of good enough growth quality for Widefield applications. But in principle, once you optimize, that gives you the most flexibility. Now, one issue though is that it's not commercially available. So unless you have a CBD reactor, you can't really buy that yet. So you can buy now from E6 bulk diamond with a lot of NVs throughout, but you can't get commercially a finite thickness layer. And that's unfortunate because if you could, then it would change the game quite significantly for Widefield applications. So how do those three techniques compare? In the regime where of hundreds to 1 micron thick layers, where all those techniques can in principle be used, which one's the best as far as sensitivity goes? So I won't go into the details of the factors in that sensitivity equations. It's very nicely reviewed in that paper here. But essentially, you have a bunch of factors. So this is the equation for the DC magnetic sensitivity. And those factors depends on essentially the nitrogen density among other things. So for instance, you have the T2 star here, the spin dephasing time, that's often scaled inversely with the nitrogen density if you don't have extra damage, extra decoherent sources. You have the photon count rate that scales proportionally, assuming some constant yield with the nitrogen density. And then you also have this factor here, which is a measurement duty cycle, how often the laser is on within your measurements. That will depend actually on T2 star because of the timing of the sequence in pulse to DMA, for instance. So all in all, it's not always obvious which way you want to go. Do you want a low nitrogen density or a high nitrogen density? So it will actually depend on a few things. And that's why we decided in the case of Widefield application, let's actually compare. In the same setup, we compare samples from different NV creation methods and see how they compare as far as sensitivity goes in those conditions. And so we compared those three methods, the HPHT ion implantation, the delta dope method, and then nitrogen implantation, either nitrogen or CN minus. And we did that on layers that we aimed for to be 100 nanometer thick. So try to get the same NV thickness and just compare the sensitivity essentially. And so I won't go into the detail of that study, it's in this paper, but the conclusion is in those plots here, which is a magnetic sensitivity to DC magnetic field on the left and to AC magnetic field doing spin echo measurement on the right. And you see each column corresponds to each method. And so what you find is that the bottom, the lowest on the graph is the best sensitivity, is the CBD, the delta doped method. So not too surprisingly, this is the one that gives you the cleanest material because you don't get too much extra damage. And also this is the one that allows you to get low nitrogen density. And in fact, turns out you prefer to be in the regime of long T2 star and low nitrogen. So sure, you'll get less photon counts, but all in all, when you examine this equation, that's what you want for Widefield. You prefer to be on the low nitrogen density side, and CBD is how you get that relatively easily. So this is the best method. However, if you look at the HPHT, the very cost-effective ion implantation in the type 1B material, some sectors, those that have low nitrogen, in fact, compare very well. You can get pretty much as good of a sensitivity. But there is some randomness. If you take bad sectors that are too dense in nitrogen, then it's getting much worse. And the nitrogen implantation clearly is always the worst by up to almost an order of magnitude compared to delta doped. And again, that's because in that regime of 100 nanometer layer, you create a lot of damage and you don't annihilate completely out. So you have worse T2 stars than you would have for the same amount of nitrogen in. And CN, it's not necessarily obvious, but it's always a little bit worse because you create even more damage because you have the carbon that is useless and yet give you more vacancies. So all in all, ideally you'd want to develop further that delta doping, make it more commercially available. Because one issue is, well, it's not easily accessible and it's still not super reproducible. Even when you have a reactor every day, is different, you might get slightly different results. So that's something we like to improve on. In the meantime, the HPHT approach is still very cost effective and relatively easily accessible. So move on to the third part, which is cryogenic operation. I'll try to go a little bit quicker on that one. So cryogenic operation is very useful, not for the sensing aspect, but for a sample. In a lot of applications, it's desirable to be able to vary temperature. And that's, for instance, when you look at charge transport in some regimes where often the interesting physics happens at low temperature. And to look at phase transition as well, magnetic superconducting phase transition, things like that. Often it happens below room temperature. So you want to have that capability. Now, somewhat surprisingly, it's been realized very early with scanning and beam microscopy. 2015, I think, was the first report of a cryogenic scanning and beam microscope. For the Widefield, it took actually much longer, and we've realized that a couple of years ago. So I'm showing here the system we've built 2 years ago, which is based on the closed cycle cryostat, and we built a Widefield microscope on top. So all the optics is on the top on that breadboard here. Very standard. You've got the laser coming down and you connect, you've got a camera on top. What you have inside the cryostat is the sample, and also the microscope objective lens is also inside the cryostat. Otherwise, it's relatively very similar to the room temperature kind of system I've shown before. So a sample we've used as a kind of test experiment was a Van der Waals 2D magnetic materials. Here, that was vanadium trioxide. So you start from ball crystal, and here, this is a type of example where you can actually transfer the sample on the diamond. And this is important because in the cryostat, we are not there yet at the stage where we can have this Widefield probe system. So we still have to do things a bit manually, transfer on the diamond or vice versa. So here we can use a Scotch tape exfoliation type of techniques and transfer directly on the diamond. Here you see the diamond with a metallic grid again, so we can see where we are. This is the optical image of the sample. You don't really see much, but once you do your ODMR and NV imaging, you get this type of image. This is a magnetic field image of flakes of this material. What's very handy is that you can convert that magnetic field into a magnetization. As long as you know the direction of that magnetization, you can do that. And that's very useful because you can compare those values of MZ here to predictions compared to theory. So very quickly, the kind of things you can do with that system, you can look at the temperature dependence. You vary the temperature in situ, and you see how the magnetization is decreasing, and so you get access to the current temperature and the critical behavior around TC. You can look at magnetic switching and look at the corrosivity of the material as a function of temperature, for instance. And you can also study the initial magnetization process, how domains grow, etc. Another example of application is to superconducting physics. So here, in that experiment, we fabricated niobium wires directly on the diamond again. We evaporate and pattern. Niobium is superconducting below 9K. And initially, we looked at the pad, the large bonding pads here. And we've looked, there's no current, just we apply a small magnetic field, 1.5 Gauss here, and we just measure the stray field penetrating through that film. And you see the expected abricos of vortices, superconducting vortices. What was surprising was that if you put too much laser power in, you quench the superconductivity at the center because that's where the laser is most intense. And that was that's kind of one of the challenges in Widefield, cryogenic Widefield microscopy, is that the laser heating is something important to consider, to take into account. And in that case, for instance, even with very modest laser power, we would have several Kelvin of heating at the center. And that can affect the physics you're looking at. So that's still an ongoing challenge that still need to be addressed, is how to mitigate laser heating in those type of experiments to make it usable in those low, in this low temperature regime. And you can use a transport, actually, the resistance of the superconducting wires to actually quantify that, and we confirm we get several Kelvin of increase under a few milliwatt of laser power. And just to illustrate another application of NV imaging is you can map the current. So now if you inject a current in that wire, when it's superconducting, it's actually a supercurrent. So with no resistance, and you can measure the magnetic field from that current and reconstruct the current density. And so here you can actually compare the superconducting regime. Those two here are when it's a supercurrent, there's no resistance locally, versus when it's normal. If you hit the thing up above TC, then it's a normal current and you get a different distribution, in fact. So it's actually a very useful technique for that, but we need to worry about laser heating. So that's still work in progress. So I'll finish with a brief outlook of what are the things we're working on and we want to improve to make that technique closer to something that could be potentially commercialized or at least deployed in a way that can be used by non-diamond experts outside the diamond lab. So we want to build on that Widefield probe concept, but we want to make it more convenient and automated. So ideally, you don't want to manually control the angle. You want just to put your sample, press a button, auto approach, auto align, and it will do the job for you. So it would look like maybe something like that. You'd have a sample on some kind of a hexapod stage, and you'd use the interference feedback, the optical feedback that I've talked about. You have fringes, etc., but you can go beyond that to get both the angle and the distance. So once you do that, then you could imagine that to be as convenient as other more standard microscopes, where you don't have to worry about what the sensor's doing. It's always fixed. So you have the diamond on that probe with a microwave integrated, and you just worry about putting your sample and getting an image. So that's the end goal anyway. And Ideally, you'd want also interchangeable optics, so you can change field of view very easily. So again, you want it to make it as versatile as possible. And the photo here is an example of where it's going. You also want to reduce the overall size and cost. So here, for instance, this is a version of a Widefield where we have an LED, so compact and also relatively inexpensive, as opposed to a laser that's a bit more bulky to integrate. So we can really make it quite compact, I think. You also want to improve the user experience. So you want fast feeding to have real-time image displaying on your screen. So that's all relatively just engineering, so to speak. On the sensor side, so I've kind of concluded that you want to develop the delta dopping further, and ideally you'd want the equivalent of what E6 has done for bulk diamond, for bulk magnetometry, but for finite thickness NV layer. And there's still sensitivity to optimize for those NV layers. For instance, one key parameter, so you have coherence, it's naturally limited ideally, so that's fine. The NV yield, I think it's one key parameter that we can still do better on for those NV layers. A few 5%, 10% typically is what you get nowadays. We should be able to get better for those NV layers. There are techniques that need to be looked at in the context of NV layers for Widefield. Spatial resolution, clearly, if it's going to be a useful technique, it has to be at the diffraction limit or close to. And so there are probably things we can do to improve what I've shown in the first part, maybe related to flatness and cleanliness of the environment. Optical aberrations is also often a limit, so there is also work to do in that space to reach that diffraction limit so that you can be really competitive against other techniques. And finally, the cryogenic operation. That's very useful for a lot of applications, not all of them, and that's yet another goal where you have to adapt, in fact, that Widefield probe concept in a way that fits in a cryostat. So ideally, you'd want to fit that into the 2-inch type of diameter that you have in standard cryostat walls. So that will require more technical development, and the laser heating is also something to be have some techniques easy to implement routinely to make sure it's actually operating at the base temperature of the cryostat. And with that, I'll thank also the students involved mainly in this work. Here I show the main one over the years, David Broadway, Scott Liddy, Alex Healy, Gabrielle, who's done the Widefield probe work, and the collaborators. Thank you.
Jean-Philippe, thank you very much for a great presentation, very comprehensive with a lot of technical details. I'm sure it's very useful for the audience. So thank you very much. So the stage is open for questions. Please just turn on your microphone and ask questions directly or type in chat room. So far, I will start with my questions. On your slide 19, where you compare sensitivity for 4 different methods of producing diamond plates. In discussion of the sensitivity, you have so-called measurement contrast, C, in the formula for sensitivity. My question is, does method of production of diamond plate influence Z parameter? So definitely there is influence on T2 star and NV density, but what's about Z parameter?
Yes, they do play a role. Yeah, absolutely. So the different method give you a different contrast. So again, the delta doping one is the best. So it's somewhat correlated with the nitrogen density. And that can be understood the more, well, especially when you get to very high densities, like in type 1b type of diamond, where you start having tunneling. It's so dense that when you excite some of the NVs, the electrons tunnel to somewhere else, and so you don't get contrast out of that one. And so often, yeah, it's getting worse the more density, and And it's also correct with the residual damage you have around. For the same reason, you have more opportunities for tunneling. And so again, the nitrogen implantation typically performs a little bit not as good. So it's not a huge difference, but you may have a factor 2 better contrast with delta doping, for instance, method, depending on the conditions. So yeah, it does play a role. So those graphs take all those factors into account, obviously. But yeah, so that's why overall less nat chain is often better, because you win on all fronts pretty much.
Please ask your questions, or otherwise I will ask mine.
I have a question. This is Abdelghani. Hi.
Hi.
Hi, Jean-Pierre. Nice presentation. So it's very nice idea. I mean, to use a diamond and approach it to the sample. So what limits this standoff 1.5 micrometers? What limits the?
So we're not 100% sure. It could be cleanliness, could be you have dust particles that, so it could be flatness essentially. It doesn't look like our sample. It looked pretty flat when we did AFM and things like that. It didn't look like there's anything big. It could be optical aberration as well. So it's possible it's a combination of several factors. I don't think there's one big limiting, maybe a bit of optical aberrations. We know that our diffraction limit first was 1 micron. So that means when we say 1.6, it's convoluted, so we don't really know. So yeah, that's a question. We haven't studied that in too much detail. We consistently get that standoff, but I'm guessing it's a combination of factors. So you'd have to improve on all of them to get below that limit. So yeah, quite question on that one. I don't really know.
Yeah, and the second question is, I know some people use like thin membranes, diamond membranes, like to thin it to few micrometer, even 1 to 2 micrometers, and then now you have the van der Waals interaction is strong, then you can bring it to your substrate. Do you think, I know in terms of cost, maybe it's expensive how you thin up, or in terms of
yeah, so that's a good idea. I haven't seen any real, well, until I see a standoff characterization, I will be able to tell, because it's sure van der Waals strong, but is that really strong given the roughness you have? I don't know, because it's a very short range interaction. So if you have like the diamond, maybe rough, 10 nanometer roughness, sample maybe even rougher. So I don't think it's going to change much. So I wouldn't think so, because you still have a strong interaction. Like the diamond looks like it's sticky, it's hard to move sometimes. And yet when you characterize the standoff, you realize you have 5 micron, because you just need 1 particle dust. So I don't think it's going to be a game changer, but who knows? Yeah.
Okay, thank you. Then very nice work.
Thank you.
We have next question from Zuzana Orchikovska. Thank you for your enlightening talk. Can you once again refer to the difference in diffraction patterns created by interface diamond sample in those 2 cases you showed on your slide?
So the question is, can I re-explain the origin of the interference, if I understand? So that's the interference between the reflection at the diamond air interface with the secondary reflection here. And if the question is, and so you have fringes, because here you have, well, the difference between 2 fringes is half a wavelength. If it's constructive here, this is an extra wavelength, and so the distance, 2 times the distance will be equal to 1 wavelength. Is that answering the question? I'm not sure.
Okay, yeah, if Zuzana will have more questions, she can type. So far, let me ask you another question. Do you prefer some special orientation of diamond plates in your measurements, like 001?
Yep, so in this particular work, that was a 100 sample, we have used, and we do use 111 diamond samples as well, which works very well as well, and is actually preferable for a lot of applications, just more convenient to measure the Z projections of magnetic field, for instance. So that's working well. You can actually buy, especially with a type 1B. So that's where the CVD growth will well, maybe even be harder to control reliably. So type 1b, it's very easy because you can buy quite large plates nowadays of type of 111 diamonds. You can get even the 4 mil plate. You can buy that, and it's not very costly in 111. And we do the same. We implant with antimony. So we've done that. We've got a lot of diamonds 111, and we use them pretty routinely as well. So we do that as well. That's working pretty well. They're not preferentially oriented. I'm not sure if it was in the question, but they're still randomly oriented. So we pick the Z orientation out of the 4. Yeah.
Thank you. And we have next question from Go Queen Wang. Thank you for the nice talk. Do you address an ensemble of NV centers to do the Widefield measurement?
Do you address what, sorry?
An ensemble of NV centers to do the Widefield measurement.
Maybe I'll open the chat because I don't know. Do you address? Yes, we address an ensemble of NV centers. That's right. So it's a dense layer. So even if you were to do confocal, you wouldn't resolve single NVs anyway. They are too closely packed, maybe 1 NV every 50 nanometer type of distance. And we eliminate a lot of them anyway. So the laser spot would be, in fact, in those type of images, you see the size, it's 200 micron, I think, here. So we have a laser spot that is bigger than that. So we eliminate a large region. And in that region, you may have millions, many millions of NVs. So it's definitely an ensemble. How do you control the size? I'm reading the question, so I'll get that one. How do you control the size of the laser spots? So if I go back to the setup, there is, so here obviously just very simplified, you come collimated and then you put a lens somewhere here, and that lens will focus the laser into the objective, and then you get a collimated beam after the objective, ideally. And so if you change the lens, how much you focus the objective, you control the laser spot. So it's all about the diameter of the incoming laser beam and that wide field lens, as it's called, that controls the laser spots. So that's how you do.
Thank you. And we have a question from Masazumi Fujiwara. Please ask your question.
Thank you very much for a nice talk. Following up on that question, and I'm interested in wide field microscope in cryogenic conditions, and I think the wide field measurement uses a lot of optical power, so that I think that it's rated. It might. How much cooling power do you need for the cryostat? I think that you are using the closed cryostat, so it doesn't matter for the consumption of helium or something like that. But I'm just interested in that.
Yeah, it doesn't matter for consumption. That's true. But still, the cooling power is limited, and so how much laser power we use? So I showed a few milliwatts. In practice, nowadays we use more like 50 milliwatts. So what was the question again?
In my experience, actually, such tens of milliwatt is very strong for cryogenic experiments. Yeah. So when I did houses cryogenic experiments with several or a few milliwatt, it's already uses a lot of helium at 4 Kelvin or something. So.
Right. So yeah, you're right. So it doesn't matter for the closed cycle. Doesn't matter. So we don't care about consumption itself, but we care about the base temperature.
Okay, but you don't see how the heating effect of heating effect by lasers, or you have enough power to cool the sample.
No, we do see heating effect. Yeah, no, there's a lot of heating happening, several Kelvin. So the sample is definitely not at the base temperature. It may be 5 Kelvin above base. So yeah, it does make a big difference. Absolutely. No, it is a problem. But it doesn't affect the operation of the cryostat. The cryostat still runs. You can still apply magnetic field with a vector magnet, etc. So that's all fine. But locally, so it's very local. So cryostat's fine. Okay. The cryostat doesn't heat, but locally the sample will have a delta T with the base temperature of the system. And yes, that's milliwatts. It is a lot. So what you want, so of course, not all of the laser power is absorbed. And so what you want is to reflect most of it. And that's kind of the idea is if you add reflection coating in the right way, maybe you can actually push that laser away from the sample. It's okay if it absorbs somewhere else, but not in the sample. You don't want the sample to hit.
Okay, thank you. Thank you for nice talk.
Thank you. Our next question is from Stefan Dix. What is the density of the NV centers in ppm of the diamond plates that you use for Widefield sensing method, roughly?
Yeah, so we don't characterize that often. We just guess it based on the coherence time, the T2. And so often with the type 1b, it's going to be of the order of 50 ppm for the sectors we use. Again, based on the T2s, and with the delta dot that we've made, is probably a bit less, 5 ppm of this order. With nitrogen implantation, when we use a technique, we aim for 50 ppm or 100 ppm peak. Yeah, so 50 ppm would be the average number we try to aim for of nitrogen. Sorry. So the question was NVs. Again, we don't know how much conversion there is, but often I would say 5%. So we don't get in this regime, especially for thin layer, it's very hard to get high yield, thin and close to the surface. So I would say a few ppms. So maybe between 1 and 5 ppm of NVs would be the typical values we have.
Thank you. And maybe I will ask also related somewhat question. What annealing temperature did you use for NV formation? And did you explore a role of annealing temperature on sensitivity?
Yes, that's a very good question, because in some conditions, annealing at higher temperature helps. So we used for a long time 1100 degrees. So a very long, slow annealing with a 1100 degrees peak. So I think 2 hours at 1100 and then a very slow ramp, etc. Which in some cases it helps to get better T2. So you don't improve the NV yield, but you just anneal out more of those paramagnetic defects. However, with type 1b, for instance, you don't necessarily want to do that, because you give more, you migrate the vacancies more, so you can create NVs more delocalized. And so if you want to create a shallow NV layer, you don't want the vacancies to actually move deeper, or at least you want some control on that. So in that case, we do 900 degrees for 2 hours, so a bit shorter. And it seems to not make a difference as far as T2s go anyway for those samples. So I think those with a lot of damage, yes, you want to anneal higher, but when it's low damage, which is the case when you do type 1b, because you don't need too many vacancies. So in that case, we do 900 typically. Yep, very good question.
Thank you very much. Please ask your questions if you have more. It seems so far everybody is happy and satisfied with the lecture and the answers. If I don't see more questions, then I would like again to thank Jean-Philippe for his beautiful talk today, for sharing his knowledge so readily, and I wish everybody happy holidays, to be energized and ready for new scientific discoveries in 2022, and hopefully we can see each other finally at some conferences and have more extended discussions face to face. So thank you very much.